for SETI, and that is speed. Right. Now, I should mention, this is a joint project with the University of California, Berkeley's radio astronomy lab. They'll be using it for conventional radio astronomy. I hate to use the word conventional, that's not a very fair adjective. They're not interested in finding out things we already know, of course. But, in any case, it is radio astronomy, but while they're doing that, we can always be looking at nearby stars in the field of view and checking them out spectrally, looking for those narrowband signals that would tell us that you have some cosmic company. Okay, now to begin with, this is faster simply because it's available 24/7. Right? That's a factor of 10 right there. But it also, because it's an array, can look at more than one spot on the sky at a time. Okay, depending on how much compute power you have behind the telescope, you can look at 3 spots on the sky, 5, 10, thousands, if you can afford the compute power. And compute power is getting cheaper every year. So this greatly speeds up the search. Right? And then, this is just a map to show you where it is. The SETI Institute is down in lovely, glamorous Mountain View, about half an hour south of here. And the observatory is up there at the top of the screen in Hat Creek, California, about 20 or 30 miles north of Mount Lassen. You can visit it, by the way. If you happen to be up in that part of the state, you ought to drive in, take a look. During the week, it's open, during business hours, and they'll be happy to have you walk around, take a look. There are 42 antennas now. Eventually, the idea is to get 350. And since this is somebody else's computer, I don't think that the animation doesn't work. But this is just an artist's conception of what the full-up array would look like, 350 antennas. Okay, we have slightly more than 10% of that now. We could have all of these done within the next 2 years if somebody in the audience would like to write the check. We know how to build them now. We can build them very quickly. So this is all money-driven. It's money-driven. This is a photo of what it looks like now. This is a picture I made about a year ago, but it looks pretty much the same. And you can see the 42 antennas there in the little building where the data processing equipment is located with the green roof back there. The remains of an earlier array, that's the north, south, east, west arm there. So there they are. They're each about 20 feet across, very cleverly designed, and a lot of electronics behind them. I'm not going to go too much into that anymore, but this graph gives you, once again, an indication of, in some sense, why we haven't found ET yet. Now, the Allen Telescope Array is already filled in here, but if you neglect that, and even if you don't, this gives you some idea of the search space, parameterized search space. Frequency in one direction, fraction of sky in another, sensitivity in the vertical direction. We barely scratched the surface looking for ET. That's really the bottom line here. This is a bit like, and this is a fairly accurate analogy actually, it's a bit like looking for megafauna in Africa, right? And so sailing to Africa, getting off the ship, walking on the shore, and looking at 1 square meter of real estate, say, well, I don't see any rhinos here, I don't see any elephants. I guess this continent is megafauna free. Well, that would be a big extrapolation from a very limited observation. It's pretty much the same with SETI. We've just begun, okay? But that's going to change, and that's what's motivating this talk, once I get into it here. This is a plot that shows how many channels we look at simultaneously, but the point is that is some sort of indicator of how fast we're going through the sky looking for ET, right? You can see Frank Drake's original experiment down there in 1960, that black dot, with 1 channel. Okay, it says 0, but this is a semi-log plot for those of you who are still conscious. And you can see that the dots are going up. In other words, the experiment is getting faster. And again, those of you who are mathematically savvy will recognize that this is a semi-log plot, which means the speed is increasing exponentially. Now, anytime you tune in the nightly news or talk shows or anything else, people talk about things improving exponentially without knowing what that means, because if you ask them, what's an exponent? They would say, well, it's somebody who's championing a cause, or something like that. I don't know what they'd say. Probably not say. But this really is exponential, right? It follows well-known Moore's law, which is one of many exponential laws in technology these days. By the way, Moore's law is, everybody thinks that that's technology, but of course it's economics, right? It's because the people who are manufacturing computers have figured that, look, it's an expensive product, and maybe we can get customers to replace them on the same time scale they replace their cars, which is another expensive product, right? So you don't replace your car every 3 months, but you don't wait 30 years, unless you're my brother, right? You replace them every 3, 4, 5, 6 years. Okay, so the question for them is, well, how are they going to get you to do that? Because, the state of California makes sure you replace your car every 5 or 6 years by not filling the potholes. But what about your computer? your computer is not subject to that kind of damage, right? It still looks as good 10 years later as it did when you bought it, really. And so what they do is they make sure it's obsolete by doubling the amount of compute power every 18 months per dollar. And you know that's true. Right after 3, 4, 5 years, if you talk about your computer at cocktail parties, you don't get any respect, right? People walk around, excuse me, I have to refresh my drink, and they walk away. Okay, so, but the point here is not so much that you have to keep replacing your computer. The point here is that SETI follows the same laws, because SETI is mostly digital electronics. If you can afford more compute power, you can look at more channels at a given time. Or if you have more compute power with an array, you can look at more than one star at a time. You can put a pixel on that star, and that star, and that star, and look at 3 at a time instead of 1 at a time. Or 10 at a time instead of 3 at a time. So compute power, which will continue to increase exponentially, more or less, at least for the next 2 decades, that's kind of the prediction, allows us to say, well, look, assuming that you finish up the Allen telescope array, or most of it, you know, how far out into space will we have looked on the basis of the Moore's Law improvement? And that's what the black line is. And so you can see by 2015, maybe we'll have looked to all the interesting star systems out to 200 light years, and then by 2025 out to 500 light years. But the interesting thing in this plot are those numbers underneath. Those are the n in the Drake equation. Right? I often say Frank Drake comes in every morning and writes this equation on the board. We don't know what it is. We've asked him. These are estimates of what n is. How many societies are out there that are broadcasting signals that could be picked up by our instruments? Now on the left, n equals 1,000,000, 10 to the 6th. That's Carl Sagan's estimate. He figured a few million. In which case, the Allen telescope array could trip across that signal by 2015. The middle estimate is Isaac Asimov's, 670,000. He estimated somehow he was able to do that to 2 decimal places. And I could tell you. Never mind. Okay, so in any case, if he's right, then it takes till 2022 or something. And Frank Drake himself figures 10,000. That's the most conservative of these estimates. And if Frank is right, then it's going to take till 2028. But the bottom line is, if any of these estimates is right, then success is not decades and decades and decades, centuries away. This is not, as it is sometimes said, like building cathedrals in the Middle Ages, where you don't finish it and your kids don't finish it, but maybe your grandkids or your great-grandkids finish it. Now you might argue that, well, there are a lot of ways this could fail, and there are. You could be missing important physics. It could be that there aren't many societies out there. All of that is possible, of course. But what I've given you are the numbers that have been promoted by the SETI enterprise itself. It's these estimates that have motivated this sort of an experiment. Okay, it isn't to say they're right. They're simply estimates, which is a euphemism for guesses, because that's what they are. Okay, but if the guesses, if you will, that have been made by people who think this is an interesting thing to do are correct, then success is this generation. Right? It's not distant, in the distant future. Okay, now having said that, let me get to the subject here. What will they be like? It doesn't matter, okay? Most of my colleagues don't seem to be terribly concerned about what they will be like. Here are some guys that look a lot like the neighborhood kids. We don't know what ET is going to be like. All we require of ET is that he build some sort of transmitter, either a radio transmitter or a giant laser or something to get in touch. That's it, right? That's the SAT test. That's all we ask for. People ask, you're looking for intelligent life. Is there intelligent life on Earth? The answer to that is inside the beltway. That's a question I get all the time. The answer is yes, because you can build a radio transmitter. And if you can't, you probably shouldn't be sitting in this audience. So we can do that. And that's all we ask of the aliens. We don't care what they look like, the color of their skin, how many fingers they've got, none of that. If they can build a radio transmitter or a powerful laser, good enough, right? That's been the assumption. Now, Hollywood, of course, does better, because Hollywood does know what the aliens look like. And Hollywood has aliens that either are good or bad. The good ones all look like kids, like little E.T. or these guys who came to give Richard Dreyfuss a joyride in their spacecraft, but didn't bother to dress for the occasion. Or the bad aliens, of which there are many more than good ones, because it makes for a more interesting story. This, of course, is... anybody know this film? Yes, sign of an ill-spent youth there. Yeah, Starship Troopers.
That's right.
Yeah, what's his name? Dutch director, actually, know the guy. But in any case, Yeah, see, Hollywood knows that you don't like certain kinds of critters. You don't like snakes, you don't like arthropods in general, except occasionally